Welcome to this walkthrough of LeetCode problem number 24, swap nodes in pairs. In this problem, we'll explore how to swap every two adjacent nodes in a linked list without modifying their values. By the end of this session, you'll gain a deeper understanding of linked list manipulation and how to develop efficient solutions. Let's dive in. In this problem, you are given a singly linked list, and your task is to swap every two adjacent nodes in the list. The key here is that you must achieve this without modifying the values stored in the nodes. Instead, you are only allowed to modify the structure of the list itself by rearranging the nodes. Let's take a look at the input and output format. The input is a singly linked list, represented by its head node. Each node in the list contains an integer value, ranging from -100 to 100, and a pointer to the next node, or null if it is the last node. The output will be a singly linked list where every two adjacent nodes have been swapped. For example, if the input list is 1, 2, 3, 4, the output list will be 2, 1, 4, 3, as adjacent nodes are swapped in pairs. Now, let's break down how the swapping works for the first example. The input is 1, 2, 3, 4. First, we swap the initial pair of nodes, which are 1 and 2. After the swap, the first two nodes become 2, 1. Next, we swap the second pair of nodes, which are 3 and 4, resulting in 4, 3. Finally, we combine these swapped pairs to form the output list 2, 1, 4, 3. In another example, if the input list is empty, that is, head equals, there are no nodes to swap. As a result, the output is also an empty list. What happens when the list has only one node? For the third example, the input is 1. Since there is just one node, there are no adjacent nodes to swap. That means the output will be the same as the input list, which is 1. This highlights an important edge case where the size of the list is too small to perform any swaps. Whether the input is empty or contains a single node, the structure of the list remains unchanged because no swapping is possible. Let's now consider the constraints and some additional edge cases. The number of nodes in the list can range from 0 to 100, and each node's value is within the range of -100 to 100. Importantly, you must solve the problem in place, meaning you can only rearrange the node connections without creating new nodes or modifying the values stored in them. For edge cases, if the list is empty, the output is also empty. If the list has a single node, it remains unchanged. For lists with an odd number of nodes, the last node remains in its original position because it doesn't have a pair to swap with. On the other hand, if the list has an even number of nodes, all nodes can be swapped pairwise. These constraints and edge cases will guide how we approach and implement the solution. To solve the problem of swapping nodes in pairs, we need to focus on rearranging the pointers between nodes rather than modifying their values. Two main approaches can be considered here. The first is the recursive approach, which leverages the natural divide-and-conquer structure of recursion. The intuition behind this method is to break the problem into smaller subproblems by focusing on one pair of nodes at a time. First, we swap the initial pair of nodes by rearranging their pointers, making the second node point to the first, and the first node point to the result of recursively swapping the rest of the list. The base case occurs when we encounter fewer than two nodes, in which case no swapping is necessary, and we simply return the head. This approach is straightforward and elegant, with a time complexity of O(n), since we visit each node once, but it comes at the cost of O(n) space due to the recursion stack. A key trade-off here is that while the recursive approach is easy to implement, its space overhead might not be ideal for very large lists. Alternatively, we can consider an iterative approach to eliminate the recursive space overhead. In the iterative approach, we avoid recursion by directly manipulating the pointers through iteration. This method is designed to be more space efficient while still achieving the same result. To simplify pointer management, we introduce a dummy node, which serves as a placeholder to help us handle edge cases, such as lists with an odd number of nodes. The steps for this approach involve using the dummy node to traverse the list in pairs. For each pair of nodes, we update their pointers to swap their positions. Once the swap is complete, we move to the next pair and repeat the process until we reach the end of the list. Finally, we return the new head of the list, which is the node following the dummy. This approach has a time complexity of O(n), as we process each node exactly once, and a space complexity of O(1), since no additional memory is used beyond a few variables. While slightly more complex to implement compared to the recursive solution, the iterative approach is highly efficient and avoids the space limitations of recursion. After evaluating both approaches, the iterative method stands out as the better choice due to its efficiency and scalability. With its O(n) time complexity and O(1) space complexity, it is well suited for handling large inputs without the risk of stack overflow. While the recursive approach is conceptually simpler and easier to write, its reliance on the recursion stack makes it less practical for real-world scenarios involving long lists. The key insight here is understanding that swapping nodes is solely about pointer manipulation, not altering the values themselves. The use of a dummy node in the iterative approach is particularly valuable, as it simplifies the process of updating pointers and ensures smooth traversal, even in edge cases like lists with an odd number of nodes. In conclusion, while the recursive approach has its merits in terms of simplicity, the iterative method strikes the best balance between clarity, efficiency, and scalability, making it the optimal strategy for solving this problem in a real-world context. The problem swap nodes in pairs asks us to rearrange a singly linked list such that every two adjacent nodes are swapped. For example, given an input list of 1-2-3-4, the output should become 2-1-4-3. If the list has an odd number of nodes, the last node remains as is since it doesn't have a pair to swap. To solve this problem, we'll use a recursive approach, which is a natural fit for breaking down the problem into smaller pieces. The core idea is to focus on swapping the first two nodes of the list and then recursively solving the rest of the list. To start, we define our base case. If the list is empty or contains just one node, there's nothing to swap, so we simply return the head as is. This ensures that the recursion stops when there are no more pairs to process, making it both efficient and easy to implement. Now, let's identify how we handle each pair of nodes. First, we use the head pointer to represent the first node of the current sublist and a second pointer to represent the second node, which is head.next. These two nodes are the ones we need to swap. Once identified, we make a recursive call to the rest of the list, starting at second.next. This recursive call processes the remaining nodes and returns the new head of the swapped sublist. With this, we ensure that the smaller problem is solved before we link the swapped nodes back together. To actually perform the swap, we update the next pointers of these two nodes. We point second.next to head, effectively reversing their order, and then point head.next to the result of the recursive call, ensuring the swapped pair is connected to the rest of the list. After the swap, the second node becomes the new head of the current sublist, which we return so that the previous recursion level can continue linking the swapped nodes together. Here's the complete recursive function in code. First, we handle the base case by checking if the list has fewer than two nodes. If so, we return the head as is. Then we identify the two nodes to swap, head and second. Next, we recursively call swap pairs for the rest of the list, starting at second.next. After the recursive call, we perform the swap by making second.next point to head, reversing their order. Finally, we return second as the new head of the current sublist. This recursive structure simplifies the problem by breaking it into smaller and more manageable pieces. Key insights here include the divide-and-conquer nature of recursion, where we solve the smaller subproblems first before linking the results. Additionally, the base case handles edge scenarios like odd-length lists by leaving the last node unchanged, ensuring correctness in all cases. This problem operates on a singly linked list, where each node contains a value and a pointer to the next node. To solve it recursively, we also rely on the implicit stack created by function calls, which keeps track of the state as we process each pair of nodes. While recursion is clean and intuitive for this problem, it can lead to stack overflow for very large inputs due to the depth of the recursive calls. Let's consider some edge cases. For an empty list, the input is none, so the output is also none, which is handled by the base case. Similarly, for a single node list, there's no pair to swap, and we simply return the single node. Finally, for an odd-length list, the last node doesn't have a pair, so it remains unchanged, as seen in the example of 1-2-3, which becomes 2-1-3. These edge cases demonstrate the robustness of the algorithm and its ability to handle different scenarios gracefully. In terms of complexity, the time complexity of this algorithm is O(n), as we visit each node exactly once while traversing the list. However, the space complexity is also O(n) due to the recursive stack, where the depth of the stack corresponds to the number of nodes in the list. While this is acceptable for small to medium-sized lists, it can become problematic for very large lists, where stack overflow might occur. For such cases, an iterative approach could be a better alternative, as it avoids recursion and reduces the space complexity to O(1). By using a loop and manually managing the node pointers, we can achieve the same results while being more memory efficient. Thus, while recursion offers simplicity and elegance, it's important to consider the trade-offs and choose the appropriate approach based on the input size and constraints. This implementation solves the swap nodes in pairs problem using a recursive approach. Here's the breakdown of the solution. 1. List node class. The list node class represents nodes in a singly linked list. Each node contains a value, val, and a reference to the next node, next. 2. Solution class. The swap pairs method inside the solution class performs the swapping operation recursively. 3. Base case. The recursion terminates if the current node, head, is none or if there is only one node left, head.next is none. In these cases, no swapping is needed, so the method simply returns the current head. 4. Recursive step. The first underscore node is set to the current head, and the second underscore node is head.next. The method then recursively calls swap pairs on the rest of the list starting from second underscore node.next. This ensures that pairs in the remaining list are swapped before reconnecting. 5. Swapping nodes. After the recursive call, the first underscore node's next pointer is updated to point to the result of the recursive call, the new head of the swapped remainder. The second underscore node's next pointer is updated to point to first underscore node. This completes the pair swap. 6. Returning the new head. After swapping the current pair, the method returns second underscore node, which becomes the new head of the swapped list. Hashtag example walkthrough. Given input 1-2-3-4. 1. The first call swaps 1 and 2. 2. A recursive call swaps 3 and 4. 3. The swapped pairs, 2-1 and 4-3, are reconnected, resulting in the output 2-1-4-3. This approach has a time complexity of O(n), because each node is visited exactly once, and a space complexity of O(n), due to the recursion stack. Here, we begin by defining the structure of a singly linked list using a static inner class called listNode. This class has three constructors: a default constructor, one that initializes the node with a specific value, and another that initializes the node with both a value and a reference to the next node. After defining the listNode class, we implement the swap pairs method, which is designed to swap every two adjacent nodes in the list. To start, we handle the base case. If the list is empty, or if it contains only one node, no swapping is required, so we simply return the head as it is. Next, we identify the first two nodes of the list, naming them first node and second node. These will be the nodes that we focus on swapping in this step. After identifying the first two nodes, we proceed with the recursive step. We call the swap pairs method on the portion of the list that starts after the second node. This ensures that the rest of the list also gets processed in pairs. Once the recursive call is made, we update the next pointer of the first node so that it points to the result of the recursive call, effectively connecting the swapped pair to the rest of the modified list. Then, we handle the actual swapping of the two nodes by making the second node point to the first node. This completes the swap for the current pair. Finally, we return the second node as the new head of the swapped pair, ensuring that the modified structure is passed back up the recursive chain. To solve the problem of swapping nodes in pairs, let's begin by considering the input list 1, 2, 3, 4. Initially, the head points to the first node, which has the value 1. The first step is to check the base case. If the head is null or if head.next is null, we know the list is either empty or has only one node, and in either case, no swapping is needed. However, in this example, neither condition is met, so we proceed. Next, we identify the two nodes to be swapped. The first underscore node is the node that head points to, which is 1, and the second underscore node is the node that follows it, which is 2. Now, we make a recursive call to the function swap pairs, using the sublist starting at second underscore node.next, which is the node with value 3. This will allow us to handle the swapping for the rest of the list first. In the recursive execution for the sublist 3, 4, the roles of first underscore node and second underscore node are now taken by the nodes with values 3 and 4, respectively. These nodes are swapped, resulting in the sublist 4-3. This completes the recursive step for the sublist. Now that the recursive call has returned the swap sublist 4-3, we proceed to swap the nodes in the current frame. First, we update the first underscore node dot next to point to the result of the recursive call. This means the node with value 1 will now point to the node with value 4. Next, we set second underscore node dot next to point to first underscore node, which links the node with value 2 to the node with value 1. By making these connections, the pair of nodes 1 and 2 are now swapped, and the resulting list becomes 2-1-4-3. The final step in this frame is to return the new head of the list, which is the second underscore node, with value 2. The output for this example is therefore 2-1-4-3. Let's look at another example, where the input list is 1, 2, 3. Once again, we begin with the initial state where head points to the first node, which has the value 1. The base case is checked, and since the list has more than one node, we proceed. We identify the nodes to be swapped. The first underscore node is 1, and the second underscore node is 2. Next, we make a recursive call to swap pairs, passing in the sublist starting at second underscore node dot next, which is the node with value 3. Now, in the recursive execution for the sublist 3, we see that the sublist has only one node. Since the base case is met here, the function returns the head, which is the node with value 3. This concludes the recursive step for the sublist. With the result of the recursive call being the single node 3, we now swap the nodes in the current frame. First, we set first underscore node dot next to point to the result of the recursive call, linking the node with value 1 to the node with value 3. Then, we update second underscore node dot next to point to first underscore node, connecting the node with value 2 to the node with value 1. This completes the swapping of the first two nodes, and the resulting list is 2-1-3. Finally, we return the second underscore node, which is now the new head of the list, with value 2. The output for this example is 2-1-3. In the final example, the input list contains only one node, 1. Here, the head points to this single node with the value 1. When we perform the base case check, we find that head.next is null, which means the list has fewer than 2 nodes. In this case, no swapping is needed, and we simply return the head as is. Therefore, the output for this example is just the single node 1. The time complexity of our solution for swapping nodes in pairs is O(n). To break this down, let's start with the recursive calls. The swap pairs function is designed to process every pair of nodes in the linked list. For each pair, the function makes a recursive call to handle the rest of the list. In the worst-case scenario, if the list contains n nodes, the function will make approximately n/2 recursive calls, since each call processes 2 nodes. Ignoring constants, this simplifies to O(n). Additionally, within each recursive call, we perform constant time operations like accessing head and head.next, and updating pointers for the nodes. These operations do not depend on the size of the input, so their contribution is O(1). Combining the number of calls with the constant work done per call, the overall time complexity is O(n). The final time complexity is determined by combining the number of recursive calls, which is O(n), with the constant work performed in each call, O(1). Multiplying these gives us O(n*(O1), which simplifies to O(n). Moving on to space complexity, the primary contributor here is the recursive stack. Each recursive call adds a new frame to the stack, and the maximum recursion depth occurs when we reach the end of the list. For a list with n nodes, there will be approximately n/2 frames on the stack, but in big O notation, constants are ignored, making the space complexity O(n). No additional data structures are used in this solution, and the memory overhead from local variables like first underscore node and second underscore node is constant, contributing O(1). Therefore, the overall space complexity is dominated by the recursion stack, which is O(n). Now let's analyze the best, average, and worst cases for this algorithm. In the best case, if the list has 0 or 1 node, no swapping is needed. The function still performs a constant time base case check, resulting in O(1) time and space. For the average case, when the list contains n nodes, the algorithm recursively processes each pair of nodes, leading to O, n, time and space. The worst case is essentially the same as the average case, as the algorithm maintains O, n, time and space even for the largest possible list. Comparing this to a brute force approach, a naive method might involve iterating through the list, manually swapping nodes, and possibly using additional memory to store intermediate results. This could increase the space complexity to O, n, for an iterative solution if auxiliary memory is used, and the pointer manipulation would be more cumbersome. In contrast, the recursive solution is elegant, avoids extra memory usage beyond the recursion stack, and achieves O, n, time complexity efficiently. An iterative approach could offer an alternative by eliminating the recursion stack, reducing the space complexity to O1. However, implementing this would require more complex pointer manipulation logic to handle the swapping of nodes directly within the loop. To mathematically justify the time complexity of the recursive approach, we can express it with the recurrence relation T, n, equals T, n2, plus O, 1, where n is the number of nodes. Solving this recurrence results in T, n, equals O, n. As for space complexity, it is directly proportional to the recursion depth, which is O, n/2, in the worst case. Simplifying this, we conclude that the space complexity remains O, n. While the iterative solution can optimize space, the recursive method strikes a balance between simplicity and performance, making it a compelling choice for this problem. When working on this problem, there are several common mistakes to watch out for. First, it's important to handle edge cases properly. For example, if the input list is empty or has only one node, there are no pairs to swap, so you need to account for these scenarios to avoid null pointer exceptions. Another frequent issue is mixing up pointers during the swapping process. Swapping nodes in a linked list involves updating multiple next pointers, and doing this in the wrong order can break the structure of the list or even cause infinite loops. To avoid this, it's helpful to plan out the pointer updates step by step before you start coding. Additionally, in recursive solutions, the base case is actually quite simple. If there are fewer than 2 nodes, you just return the head. Overcomplicating this can lead to unnecessary conditions or even stack overflow in some cases. Finally, for iterative solutions, don't forget the need to reconnect the last node of the previous pair to the first node of the current pair. Overlooking this detail can leave your list in a disconnected state, so it's crucial to manage these connections carefully. Another common area to consider is space optimization, especially in iterative solutions. While recursive approaches naturally use O, n, space due to the call stack, iterative solutions can achieve O, 1, space. However, beginners sometimes introduce extra data structures, like arrays, to track nodes, which defeats the purpose of optimizing for space. Now, in the context of interviews, this problem is a great opportunity to showcase your understanding of linked list manipulation. Demonstrating clean pointer updates and recursive logic can leave a good impression. Be prepared for follow-up questions that expand on the problem, such as swapping every k nodes, as seen in LeetCode number 25. Discussing edge cases, like an empty list or an odd-length list, with your interviewer before you start coding can demonstrate a thoughtful and thorough approach. Finally, it's worth being ready to explain trade-offs, such as the difference in space complexity between recursive and iterative methods. This shows not only your ability to implement solutions but also to evaluate their efficiency. This problem also connects to several related linked list problems that you might encounter. For instance, LeetCode number 206, which focuses on reversing the entire linked list, is a fundamental operation and a great precursor to understanding more advanced manipulations. Then, there's LeetCode number 25, where you reverse nodes in groups of k instead of pairs, a more complex variation that builds on the same concepts. Another related problem is LeetCode number 92, which involves reversing a sublist within a linked list. This requires precise pointer manipulation and a deep understanding of how to manage node connections. Lastly, LeetCode number 328 challenges you to rearrange nodes based on their positions, such as grouping odd-indexed nodes together followed by even-indexed ones. Each of these problems reinforces your skills in linked list operations and prepares you for variations in interviews. When solving this problem, it's also important to weigh the trade-offs between different approaches. The recursive approach is often admired for its elegance and concise implementation. If you're comfortable with recursion, it can make your solution very clean. However, it comes with the disadvantage of O(n) space due to the call stack, which can be a problem for very large lists. On the other hand, the iterative approach avoids the stack entirely and achieves O(1) space, making it more efficient for large inputs. The trade-off here is that it typically requires more code and careful pointer management, which can be tricky for beginners. Another useful technique is to introduce a dummy node before the head of the list. This simplifies edge case handling, such as swapping the first pair, by providing a consistent starting point. While it adds a touch of complexity to your code, the dummy node can make the logic much clearer and easier to follow. Each of these approaches has its strengths, so choosing the right one depends on the context and constraints of the problem. Great job! To summarize, we solved the problem by swapping adjacent nodes in a linked list, focusing on both efficiency and clarity. Remember the importance of understanding both iterative and recursive approaches for linked list problems. Thanks for tuning in, and don't forget to like, subscribe, and explore more solutions with us. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!